Okay, someone asked a question about question 7.2, and it says, what's the rate law for the following SN2 reaction? Now, before we look at this specific problem, let's look at a generic one. So if we have, for instance, an alkyl bromide, and we add to that a nucleophile, a negatively charged nucleophile, a generic one, what we're going to end up doing is we're going to end up substituting the bromide for the nucleophile. And so this reaction, when one nucleophile substitutes and the other group becomes a nucleophile, this is what is called nucleophilic substitution, or SN. When the way that this reaction occurs is the nucleophile will take its negative charge, and its negative charge corresponds to a lone pair of electrons. It's going to take that and it's going to donate it to the carbon to form the carbon nucleophile bond. If it stops there, you have 5 bonds to a carbon, so at the same time you're forming that bond, the pair of electrons in the carbon-bromine bond needs to go to bromine. And so that's how you end up forming this carbon nucleophile bond and a Br minus. And the Br minus, since it's leaving, this is sometimes called the leaving group. So the halogen that is leaving is called the leaving group. So in this specific case, if we look at this, what we have is we have a CH3, CH2, CH2, Br. That's that molecule. The nucleophile is sodium cyanide, but remember that sodium cyanide has an Na plus and a Cn minus. It's the Cn minus that's going to be my nucleophile in this reaction. And so what's happening is the Cn minus is coming in, donating its pair of electrons, and kicking off the bromine. It's taking its pair of electrons. So they also forgot over here to put a Br minus. So this is an SN2 reaction, and what it means is that the reaction is bimolecular. And that means that in this reaction up here, the rate equation is found to be the rate constant times the concentration of the alkyl bromide to the first power times the concentration of the nucleophile also to the first power. Okay, that's what was determined experimentally, and they did that by basically determining the rate of the reaction and looking at the concentration of the alkyl halide and the concentration of the nucleophile. And what they did was, I'll just give you some sample data. Maybe they found the rate was 10 when they used 1 molar and 1 molar solutions. When they doubled the concentration of the alkyl halide but kept the nucleophile, the concentration the same, they found that the rate doubled. And so that means that when the rate doubles, when you double the concentration of the alkyl halide, that means that it mathematically is to the first power. So anything to the first power, if you double the concentration of alkyl halide, you will double the rate. Then what they did was they decided to double the rate of the nucleophile, holding the concentration of the alkyl halide the same, and they found that the rate also doubled. And so that means mathematically that this rate equation would have the nucleophile to the first power, so that when you double the concentration of the nucleophile, you double the rate. And as a double check, when they doubled the concentration of the alkyl halide and they doubled the concentration of the nucleophile, what they ended up doing was finding out that the rate would then equal double the concentration times double the concentration, and if these were truly to the first power, then that means that the overall rate should have been 4 times, which means they found that the rate was 40 when they doubled the concentration of each. So this is a review basically of general chemistry and how you determine rate equations, which in general chemistry you were probably told over and over again that has to be done from rate data, kinetic data, as is shown here. So then if the reaction is first order in one reactant and it's first order, so it would be said to be first order in alkyl halide, first order in nucleophile. Overall, the reaction is said to be second order, and that's where the SN2 part comes into play, because this is has second order kinetics overall. Now what that means on the molecular level is that means in the rate determining step that you have 2 molecules that are reacting together. And so in the rate determining step, your alkyl halide is reacting with your nucleophile molecule, and that's what makes this what is called bimolecular. So whenever you have a rate equation of 2 molecules where each is to the first power, that means that the reaction is second order, which means that the reaction itself is bimolecular, and that means that the kinetic rate is dependent upon 2 molecules' concentrations. And that means that actually 2 molecules are reacting in the rate determining step. So that's where the 2 comes from, is the fact that this is now bimolecular. This is now bimolecular nucleophilic substitution. Okay, so if we go back to our problem 7.2, it's asking us for the rate equation. And so, what are my 2 reactants? This is my first reactant. The sodium cyanide is my second reactant. So what is the IUPAC name of this molecule? Well, this is 1-bromo propane is its name. And so the rate equation here is going to equal a rate constant times the concentration of the alkyl halide, which is 1-bromopropane, times the concentration of the nucleophile, which in this case comes from the sodium cyanide. And so in this case, answer D is the correct one, because it has sodium cyanide to the first power times the alkyl halide, which in this case is 1-bromopropane to the first power. Okay, and so that's how we look at the rate equation for an SN2 reaction.